At 0630 hours on April 23, 1945, Lieutenant Colonel John Wilson stood on the southern bank of the Po River near Fellonica, Italy, watching his Royal Engineers unload the first steel panels from 3-ton trucks. The river stretched 270 feet across, dark water moving fast with alpine snowmelt. On the far bank, scattered German units were desperately trying to escape north toward the Austrian border. Wilson had been given an impossible order: build a bridge capable of carrying 40-ton tanks across this river in less than 12 hours. Behind him, 20,000 Allied troops were waiting to cross. Ahead of him, the entire German 10th Army was trying to retreat. If his engineers could get a bridge up fast enough, they could trap thousands of German soldiers before they reached the Alps. The race was on. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you're watching from today. Wilson was a veteran of the Italian campaign. He had been building bridges under fire since Sicily in 1943. He knew every type of military bridge the British Army used. But what he was about to build was different. It was called a Bailey Bridge, and it was about to prove itself as one of the most decisive engineering innovations of the entire war. The Germans retreating across the Po had no idea that Allied engineers possessed a weapon that could be assembled faster than they could run. The morning of April 23rd was clear and cold. The Po Valley stretched flat and green in every direction. The German retreat had turned into chaos. Wehrmacht units that had fought skillfully in the mountains for 18 months were now streaming north in disorganized columns, abandoning equipment, discarding weapons, trying desperately to reach the Adige River defense line, 30 miles north. Every bridge they had controlled across the Po had been destroyed. German engineers had blown the spans methodically as they retreated, dropping steel girders into the water, cratering approach roads, and mining the riverbanks. It was textbook defensive demolition. What they had not counted on was how fast the Allies could replace those bridges. The strategic situation in Italy had reached its culmination. Since landing at Salerno in September 1943, Allied forces had fought their way north through some of the most difficult terrain in Europe. The Gothic Line, the Gustav Line, Monte Cassino, Anzio. Every mountain ridge was a fortress. Every river valley was a killing ground. German Field Marshal Albert Kesselring had promised Hitler he would make the Allies pay for every foot of Italian soil. He had kept that promise. By April 1945, the Italian campaign had cost the Allies over 300,000 casualties. But now the Germans were out of the mountains. The Po Valley was flat, open tank country. Allied armor could move fast here. The 8th Army, consisting of British, Canadian, Polish, Indian, and New Zealand divisions, had broken through the Argenta Gap on April 19th. The American 5th Army had captured Bologna on April 21st. German defensive lines that should have held for weeks collapsed in days. Wehrmacht units that had fought stubbornly in prepared positions were now retreating in daylight, exposed to Allied fighter bombers that hunted them mercilessly. The German plan was simple: get across the Po River, blow every bridge behind them, establish a new defense line along the Adige River, and hold long enough for Army Group C to withdraw into Austria through the Brenner Pass. It was a fighting retreat, and if executed properly, most of the German forces in Italy could escape to fight another day. The Po River was their shield. Without bridges, Allied armor could not pursue. By the time Allied engineers built new crossings, German forces would be dug in along the Adige. That calculation depended on one assumption: that building a bridge took time. Traditional military bridging required specialized equipment, heavy cranes, weeks of preparation. The Germans had studied Allied bridging capabilities. They knew about pontoon bridges, treadway bridges, fixed-span bridges. All of them took time to construct, time the Germans would use to escape. What they did not know was that British and American engineers had been using a completely different type of bridge since 1942. A bridge that could be built by hand, without cranes, without specialized tools, strong enough to carry the heaviest tanks, and fast enough to be operational in hours instead of days. The Bailey Bridge was the brainchild of Donald Bailey, a quiet civil engineer from Rotherham, Yorkshire. He was not a famous inventor. He was not a military hero. He was a civilian employee of the British War Office, working at the Experimental Bridging Establishment in Christchurch, Dorset. He had joined the establishment in 1928, after graduating from the University of Sheffield with an engineering degree. His job was to test and evaluate portable military bridges, the kind used to get troops across rivers during combat operations. By 1940, the bridges the British Army was using were inadequate. They had been designed during World War I, when the heaviest tanks weighed 10 tons. The new generation of British tanks, the Matilda and the Churchill, weighed 40 tons. Existing portable bridges could not support them. The British military faced a crisis. How do you conduct mobile warfare when your bridges cannot carry your tanks? The solution could not take years to develop. War had already begun. Poland had fallen. France would fall soon. Britain needed a new bridge immediately. Bailey had been thinking about this problem for years. In 1936, he had sketched an early concept for a modular bridge system using standardized rectangular panels. The War Office had shown no interest, but in late 1940, with German panzer divisions sweeping across France and British forces evacuating from Dunkirk, the need for a better bridge became urgent. The War Office convened a conference on military bridging. Bailey attended. He brought his sketches. The design he presented was revolutionary in its simplicity. Instead of heavy steel girders that required cranes to lift, Bailey proposed using small, prefabricated panels. Each panel would be 10 feet long and 5 feet high, made of welded steel trusses. The panels would weigh 600 pounds, light enough for 6 men to carry. The panels would connect end-to-end using steel pins hammered through holes at the corners. To increase strength, panels could be stacked vertically or placed side by side. A single-panel bridge could carry light vehicles. A double or triple-panel bridge could carry tanks. The entire system would use standardized components that fit together like a giant construction set. The key innovation was the panel itself. It was not a solid beam. It was a truss, a lattice of steel members arranged in a specific geometric pattern to distribute weight efficiently. Every panel was identical. Every pin was identical. Every connection method was identical. And that meant panels manufactured in different factories would still fit together perfectly. It meant damaged panels could be replaced instantly. It meant engineers in the field could adapt bridge length and strength by adding or removing panels without redesigning anything. The War Office approved Bailey's design in February 1941. The Ministry of Supply was ordered to produce a full-scale prototype by May. That timeline was impossibly tight. Normal military procurement took years. Bailey and his team had 3 months. They worked around the clock. The design was refined by Major Ralph Freeman, who had designed the Sydney Harbour Bridge in Australia, and Major H.A.T. Jarrett Kerr, both Royal Engineers with extensive structural engineering experience. Together, they finalized the specifications for every component. The first prototype was tested in December 1940. Engineers built the bridge in a field near Christchurch, laying it just 2 feet above the ground. The test was brutal. Drive the heaviest tank available onto the bridge and see if it collapsed. They used a Mark V tank from World War I, filled with pig iron to increase its weight, and parked it in the center of the span. The bridge held. They added smaller contemporary tanks on top. The bridge still held. They loaded it until the steel groaned. Only then did it fail, and the failure point was well above the design specifications. Full production began in July 1941. The challenge was immense. Britain was at war, steel was rationed. Every major engineering firm was already working on urgent war contracts. Bailey's bridge required hundreds of thousands of steel panels, but there was no capacity to manufacture them using traditional methods. The solution was to spread the work across the entire British industrial base. Over 650 firms were contracted to produce bridge components. Window manufacturers, greenhouse builders, bedstead factories. Any company with metalworking capability was brought into the program. By the end of 1941, Bailey bridges were entering service with Royal Engineer units. The first operational deployment came in Tunisia in November 1942. when the 237th Field Company Royal Engineers built a Bailey Bridge over the Majerda River near Medjez El Bab. The bridge was constructed at night to avoid German artillery fire. It was operational by dawn. Allied tanks rolled across it before German commanders even knew it existed. The first Bailey Bridge, built under direct enemy fire, was constructed at Leonforte in Sicily by members of the 3rd Field Company Royal Canadian Engineers. German machine guns raked the construction site. Mortars fell among the working parties. Engineers were hit, but the bridge went up anyway. Panels were carried forward. Pins were hammered in. The bridge extended across the gap. Tanks crossed. The Americans immediately recognized the Bailey Bridge's value. The United States licensed the design and began mass production. By 1944, American factories were producing 25,000 Bailey panels per month. The bridge became the standard tactical bridge for all Allied armies. British, Canadian, American, Polish, Indian, New Zealand, South African forces all used it. In Italy alone, Allied forces constructed over 2,500 Bailey bridges between 1943 and 1945. That was 55 miles of bridging at an average span length of 100 feet. The speed of construction was what made the Bailey Bridge devastating. A 40-man engineer company could build a simple single-span bridge in 3 to 4 hours. A more complex multi-span bridge could be completed in 12 to 24 hours. Compare that to traditional fixed bridges, which took weeks, or pontoon bridges, which required specialized boats and flotation equipment. The Bailey could be built anywhere, over any obstacle, in any weather, under fire. The construction method was elegant. Engineers would assemble panels on the near bank, connecting them end to end. The assembled bridge section would rest on rollers. As more panels were added at the rear, the entire structure would be pushed forward across the gap. The leading edge of the bridge would be angled upward using wooden wedges like a launch ramp. When the far side was reached, the wedges would be removed and the bridge would settle into place. No crane required, no heavy equipment, just soldiers, steel panels, and determination. German forces learned to fear the Bailey Bridge. Every time they destroyed a bridge, a Bailey would replace it within hours. Wehrmacht demolition teams would blow a span in the morning. By evening, Allied tanks would be rolling across a new Bailey Bridge at the same location. It was psychological warfare. The Germans could not break contact. They could not establish defensive lines. The moment they destroyed infrastructure, Allied engineers rebuilt it faster than they could retreat. Field Marshal Bernard Montgomery, commander of the British 8th Army and later the 21st Army Group, credited the Bailey Bridge as essential to victory. He stated publicly that without Bailey bridging, he could never have maintained the speed and tempo of forward movement in Italy and Northwest Europe. General Dwight Eisenhower, Supreme Allied Commander, called it one of the 3 most important technological developments of the war. It ranked alongside radar and the proximity fuse in strategic significance. By April 1945, Bailey bridges had become routine. Royal Engineer units could construct them in their sleep. American engineer battalions had perfected rapid deployment techniques. The longest Bailey Bridge built during the war stretched 1,126 feet across the Sangro River in Italy. Another spanned 1,154 feet over the Chindwin River in Burma. Floating Bailey bridges, supported on pontoons, could cross rivers of almost any width. The bridges were everywhere. They were the arteries of Allied logistics. And now, on the morning of April the 23rd, 1945, Lieutenant Colonel Wilson was about to use that capability to trap an entire German army. The German 10th Army was in full retreat. Divisions that had fought skillfully in the Apennine Mountains were streaming north across the Po Valley. The 14th Army, which had held the western sector of the Gothic Line, was also pulling back. Together, these forces represented the last cohesive German military presence in Italy. If they reached the Adige River and established a new defensive line, they could hold for weeks, possibly months. If they escaped into Austria through the Brenner Pass, they could reinforce the defense of southern Germany. Allied strategy was to prevent that escape. The plan, called Operation Grapeshot, was designed to trap German forces south of the Po River and destroy them before they could retreat. The American Fifth Army under General Lucian Truscott would drive north from Boulogne, cutting off German escape routes. In the west, the British Eighth Army under General Richard McCreary would advance from the east, sealing the Adriatic flank. Both armies would converge at Bondeno and Ferrara, 30 miles north of Bologna, creating a pocket that would trap German divisions south of the Po. The critical factor was speed. Allied forces had to reach the Po River before the Germans could cross it. Then, Allied engineers had to build bridges faster than German rearguards could destroy them. If the Allies hesitated, if they paused to consolidate their gains, the Germans would escape. But if Allied armor could cross the Po within hours of reaching it, the German retreat would turn into a rout. Wilson's orders reflected that urgency. His engineering company had been attached to the 6th South African Armoured Division, which was spearheading the British advance in the eastern sector. The South Africans had reached Phalonica on the Po's southern bank early on April 23rd. German rearguards had blown the bridge there 2 days earlier. The nearest intact crossing was 15 miles away. If the South Africans waited for pontoon bridges or treadway spans, they would lose a full day. By then, thousands of German soldiers would have escaped north. Wilson's solution was a Bailey Bridge. His company had the components. They had trained personnel. They had done this dozens of times before, but never under this much pressure, never with an entire army waiting to cross, never with the outcome of the Italian campaign hanging in the balance. The first step was reconnaissance. Wilson and his section commanders walked the riverbank, studying the crossing site. The Po was 270 feet wide at Phalonica. The current was fast, approximately 5 miles per hour. The bottom was muddy, unsuitable for pontoon supports. The banks were steep but stable. The approach roads were intact. German artillery fire had been sporadic since the South Africans secured the south bank. Enemy observers across the river had pulled back. Conditions were as good as they were going to get. Wilson calculated what he needed. A 270-foot span would require 27 Bailey panels in a single line. But a single-panel bridge could only support light vehicles. To carry 40-ton tanks, he would need a triple-panel configuration. 3 panels side by side, A for width, stacked too high for strength. That meant 54 panels total for the main span, plus approach ramps on both banks. He had the panels. They were stacked on trucks 200 yards behind the riverbank. The limiting factor was time. Construction began at 0700 hours. The engineer company is divided into working parties. One party cleared the approach road and prepared the launch site. Another party began assembling panels on rollers near the bank. A third party positioned wooden launching wedges to angle the bridge upward as it extended over the water. The work was methodical. Every man knew his job. Panel carriers moved forward with 6 men per panel, lifting bars inserted through holes in the steel frames. The panels were lowered onto the launch platform. Pins were hammered through the corner holes. Bolts were tightened. The structure extended. The noise was constant. Hammers striking steel, bolts being wrenched tight. Trucks arriving with more panels, officers calling out measurements, the smell of welding as reinforcing plates were added. Every 10 minutes, another 10-foot section was complete. The bridge grew longer. At 0830, the assembled span was 50 feet long. At 0900, it was 80 feet. The pace never slowed. German observers on the far bank watched through binoculars. They radioed back to their artillery batteries. At 0945, the first German shells landed near the construction site. The range was long, over a mile. The shells exploded in the fields behind Wilson's position. Shrapnel whistled overhead. The engineers kept working. More shells came in, walking closer. One landed 30 yards from the riverbank, throwing dirt into the air. Still, the engineers worked. Allied counter-battery fire engaged the German guns. British artillery had located the German firing positions using sound-ranging equipment. Within minutes, British 25-pounders were dropping shells on the German batteries. The incoming fire slackened. Wilson's men kept assembling panels. By 1000 hours, the bridge was 120 feet long, extending nearly halfway across the river. The structure hung suspended over the water, supported only by the near bank. The leading edge was angled upward at 20 degrees, resting on the launch wedges. As each new panel was added at the rear, the entire bridge was pushed forward on rollers. The weight was tremendous, thousands of pounds of steel moving inch by inch across the gap. The technique required precise coordination. Too much force, and the bridge could buckle. Too little, and it would not move. Engineers used tank recovery vehicles as pushers, their engines straining to move the mass forward. Slowly, the bridge extended. At 10:30, it was 150 feet. At 1100, 180 feet. The far bank was approaching. That was when the German Stuka dive bombers appeared. Two aircraft, remnants of the Luftwaffe's once mighty fleet, came in low from the north. Air raid sirens wailed. Allied anti-aircraft guns opened fire. The Stukas ignored the flak and dove on the bridge. Their bombs fell. One exploded in the river, sending up a geyser of water. The other hit the south approach road, cratering the pavement 50 feet behind the construction site. Neither bomb struck the bridge itself. The Stukas climbed away, trailing smoke from flak damage. Wilson's engineers resumed work. At 11:45, the bridge reached the far bank. The leading edge touched down on the northern approach. Engineers rushed forward to secure the connections. Wooden wedges were pulled out. The bridge settled level. Approach ramps were added on both ends. Steel decking was laid across the panels to create the road surface. At 1300 hours, less than 12 hours after construction began, the bridge was complete. Wilson walked across it first, testing the structure. The steel panels flexed slightly under his weight, but held firm. He signaled back to the south bank. The first vehicles began to cross. Scout cars, jeeps, trucks carrying infantry. Then the tanks. Sherman tanks, 30 tons each, rolled onto the Bailey Bridge. The structure groaned but held, one after another. The tanks crossed. By 1330, an entire armoured brigade was across the Po River at Salonika. The South African Armoured Division pushed north immediately. German rearguards, still trying to organize a defensive line, found themselves outflanked. Allied tanks were already north of the Po. The German retreat accelerated. Units that had been withdrawing in good order broke and ran. Equipment was abandoned. Artillery pieces were spiked. Ammunition dumps were destroyed. The Wehrmacht's retreat turned into a rout. Similar scenes were playing out across the entire Po Valley. American engineers from the 10th Mountain Division built a Bailey Bridge at Somaide, 40 miles west of Salonika. British engineers from the 78th Division erected another span near Ponte Lagoscuro. Canadian engineers threw a bridge across at Ostiglia. Polish engineers built one at Salonika. Every crossing took less than 24 hours. Every crossing released thousands more Allied troops into the German rear. The Germans had no answer. They could destroy bridges faster than traditional engineering could replace them, but they could not destroy them faster than Bailey bridges could be built. Wehrmacht demolition teams were overwhelmed. For every bridge they blew, two more appeared elsewhere. The Po River, which should have been an impenetrable barrier, became a temporary inconvenience. Allied armor crossed wherever and whenever commanders wanted. By April 25th, 5 Allied divisions were across the Po. By April 26th, the number had grown to 10. German forces south of the river found themselves trapped. The Adige River defense line, which they had hoped to man, was now behind Allied spearheads. The Brenner Pass, their last escape route into Austria, was cut off. Entire divisions surrendered. The German 10th Army ceased to exist as a fighting force. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The final statistics were staggering. Between April 23rd and April 30th, 1945, Allied engineers built over 40 Bailey bridges across the Po River and its tributaries. The bridges varied in length from 100 feet to over 1,000 feet. The longest, built by the British at Ostiglia, was 1,370 feet long, supported on 13 pile piers, constructed in just 36 hours. That bridge alone allowed 2 entire divisions to cross the Po in a single day. The German Army Group C, which had numbered over 600,000 men in early April, was effectively destroyed as a fighting force by the end of the month. Over 110,000 German soldiers were killed or wounded. Over 345,000 surrendered. The Italian campaign, which had dragged on for 20 months through mountains and fortified lines, ended in 7 days once Allied forces reached the Po Valley. The Bailey Bridge was not the only factor in that victory, but it was decisive. Without rapid bridging capability, the Allied advance would have stalled at the Po River. German forces would have escaped. The war in Italy would have continued. Donald Bailey never sought public recognition for his invention. He remained a civilian employee of the British War Office throughout the war, working quietly at the experimental bridging establishment. He was knighted in 1946, becoming Sir Donald Bailey, but he rarely discussed his achievement publicly. In interviews late in his life, he insisted that the bridge was a team effort involving dozens of engineers and thousands of factory workers. He deflected credit to the Royal Engineers, who built the bridges under fire, and the soldiers who crossed them into battle. But military commanders understood what Bailey had created. Field Marshal Montgomery wrote after the war that the Bailey Bridge was the finest piece of military engineering in the entire conflict. General George Patton, commanding the United States Third Army in Europe, called it the most important tactical development of the war. Soviet Marshal Georgy Zhukov, after seeing Bailey bridges used by Allied forces, ordered immediate production of a Soviet copy called the East Bridge. Every major combatant nation recognized that Bailey had fundamentally changed military engineering. The bridge's influence extended far beyond World War II. Bailey bridges remained in military service for decades. During the Korean War, American and British engineers built hundreds of Bailey spans to maintain supply lines through mountainous terrain. In Vietnam, the United States Army used Bailey bridges extensively. Modern military forces still use updated versions of the same basic design. The medium girder bridge, used by NATO forces today, is a direct descendant of Bailey's original concept. Modular panels, standardized components, rapid assembly by hand. The civilian applications were equally important. After the war, thousands of surplus Bailey bridges were sold to governments worldwide. They became permanent road bridges in countries recovering from wartime destruction. In remote regions lacking heavy construction equipment, Bailey bridges provided the only practical way to cross rivers and gorges. The design was so versatile that it could be adapted for almost any situation. Short spans, long spans, heavy loads, light loads, temporary construction, permanent installation. Today, Bailey bridges are manufactured in over 30 countries. They are used for disaster relief, providing emergency river crossings after floods and earthquakes. They are used in mining operations, creating access routes through difficult terrain. They are used in developing nations, connecting isolated communities to transportation networks. The basic panel design that Donald Bailey sketched in 1936 remains fundamentally unchanged. It works as well now as it did in 1945. But in April 1945, as Lieutenant Colonel Wilson watched South African tanks roll across his bridge at Felonica, none of that future was visible. What was visible was immediate and tactical. German soldiers on the far bank running north, Allied tanks pursuing them, a retreat turning into a rout. The Po River, which should have been a barrier, crossed in hours instead of weeks. The German commanders trapped south of the Po understood what had happened. They had lost the race. Their careful demolition plans, their prepared defensive lines, their timetables for withdrawal all became irrelevant the moment Allied engineers could build bridges faster than they could destroy them. The Wehrmacht had faced superior firepower before. They had fought against overwhelming numbers. But they had never faced an enemy who could rebuild infrastructure faster than it could be demolished. German after-action reports filed in late April 1945 repeatedly mentioned Allied bridging capabilities as a critical factor in their defeat. One German division commander noted that his unit had destroyed 6 bridges during their retreat, only to find Allied tanks crossing at all 6 locations within 24 hours. Another reported that his rearguard had blown a bridge in the morning and watched Allied engineers complete a replacement bridge by sunset the same day. The psychological impact was devastating. German soldiers realized they could not escape. No matter how fast they moved, Allied engineers were faster. The Bailey Bridge had done something no weapon could do. It had eliminated time as a defensive resource. In traditional warfare, destroying infrastructure bought time. An army could blow a bridge and gain days or weeks while the enemy figured out how to cross. That delay allowed repositioning forces, establishing new defensive lines, bringing up reinforcements. The Bailey Bridge compressed that delay from weeks to hours. Suddenly, destroying bridges accomplished nothing except temporary inconvenience. This capability changed strategic calculations. Allied commanders could plan operations knowing that rivers were not obstacles. They could launch offensives without waiting for bridging equipment to arrive. They could exploit breakthroughs immediately because engineers could throw bridges across anything in hours. The operational tempo increased dramatically. Attacks that would have paused at every water obstacle now flowed continuously. Defensive lines that relied on rivers as barriers became indefensible. The German military had no equivalent capability. Their bridging equipment was heavier, slower, and required specialized training to operate. German engineers could build excellent bridges, given time and resources, but they could not match the speed of Bailey. Construction. Wehrmacht field commanders repeatedly requested portable bridging equipment similar to what the Allies used, but German industry never produced it. The few attempts to copy the Bailey Bridge came too late to matter. In the final weeks of the war in Europe, Bailey bridges appeared everywhere. American engineers built them across the Rhine at multiple points after the Remagen Bridge collapsed. British engineers threw them across the Elbe River in northern Germany. Canadian engineers used them throughout Holland. The bridges became so common that soldiers stopped noticing them. They were just there, appearing whenever needed, enabling movement, sustaining advances. The numbers reveal the scale. Between D-Day in June 1944 and VE Day in May 1945, Allied forces in Northwest Europe built over 4,000 Bailey bridges. That represented over 80 miles of tactical bridging. In Italy, during the same period, another 2,500 Bailey bridges were constructed. In Burma and the China-Burma-India theater, British and American engineers built over 1,500 more. Globally, Allied forces erected approximately 8,000 Bailey bridges during the war. Each one was built by hand. Each one was assembled from identical panels manufactured in factories across Britain and America. The production statistics were equally impressive. British factories produced over 200,000 Bailey panels during the war. American factories produced over 600,000. That represented roughly 250 miles of bridge components, enough to span the English Channel 5 times. The steel required for this production exceeded 300,000 tons, equivalent to 30 battleships. Every panel was inspected, every component was tested. Quality control was absolute because lives depended on it. The men who built these bridges under fire deserved recognition alongside the engineers who designed them. Royal engineers, American Army engineers, Canadian engineers, all of them worked under conditions that would terrify civilian construction crews. They built bridges while German artillery fired at them. They assembled panels while machine guns raked the work sites. They pushed structures across rivers while enemy snipers targeted anyone who stood up. The casualty rates among engineer units were significant. In Italy alone, British and American engineer battalions suffered over 12,000 casualties between 1943 and 1945. Many of those casualties occurred during bridge construction. A German shell landing among a Bailey Bridge working party could kill or wound a dozen men instantly. But the bridges kept going up. When casualties occurred, replacement crews stepped forward, panels kept moving, bridges kept extending. The engineers who built the Follonica Bridge on April 23rd were typical of these units. Lieutenant Colonel Wilson had joined the Royal Engineers in 1938. He had trained on Bailey bridges in 1942. He had built his first combat bridge in Tunisia in 1943. He had constructed bridges in Sicily, at Salerno, at Monte Cassino, across the Garigliano River, the Rapido River, the Arno River. By April 1945, he had overseen the construction of over 30 Bailey bridges under combat conditions. His company sergeant major, a Yorkshire miner named Thomas Hewitt, had been building bridges since North Africa. Hewitt knew every panel type, every connection method, every construction technique. He could estimate bridge requirements by looking at a gap. He could calculate load capacities in his head. He trained new engineers by taking them to construction sites and showing them how panels fit together. His hands were scarred from hammering steel pins. His hearing was damaged from artillery fire, but he could still assemble a Bailey panel faster than men half his age. The sappers, the enlisted engineers, came from every background. Farmers, factory workers, miners, shop clerks, most had no engineering training before joining the army. They learned bridge construction through practice, building span after span under progressively more difficult conditions. They became experts through repetition. After building 50 bridges, the work became automatic. Panels went up, pins went in, bolts got tightened, the bridge extended. These men rarely appeared in official histories. Their names were not recorded in after-action reports. They received no medals for routine bridge construction, only for actions above and beyond normal duties. But they were the ones who made the Bailey Bridge system work. Without skilled, disciplined crews willing to work under fire, the bridges would not have gone up. Without sergeants who could organize working parties and maintain pace under pressure, construction would have failed. The Wehrmacht Bridge was built by 120 men working for 12 hours. 20 of them were veterans with over 2 years of bridge building experience. 40 were reinforcements who had joined the unit in the past 6 months. 60 were recently arrived replacements with minimal training. They all worked together because the system was designed for that. Experienced men handled critical connections. New men carried panels. Everyone contributed. That inclusiveness was one of Bailey's key innovations. Traditional bridging required specialized skills. Only trained engineers could operate heavy equipment or calculate structural loads. The Bailey Bridge democratized engineering. Anyone physically capable could carry panels. Anyone could hammer pins. The design was so simple that soldiers could learn basic assembly in a single training session. Advanced techniques like building triple panel configurations or launching long spans required experience. But the fundamentals were accessible to everyone. This accessibility meant that engineer units could absorb casualties and continue operating. If experienced men were killed or wounded, less experienced soldiers could step up. The work might slow down, but it would not stop. Compare that to specialized bridging equipment requiring trained operators. Lose the operators, and the equipment became useless. The Bailey Bridge was operator independent. As long as panels and strong backs were available, bridges could be built. The Germans never fully grasped this advantage. German intelligence reports analyzing Allied bridging operations focused on the bridges themselves, their strength, their span capability, their construction speed. What they missed was the human factor. Allied engineer units could sustain bridge construction despite casualties because the system did not depend on a few key individuals. German bridging, with its emphasis on specialized equipment, was more vulnerable to disruption. By April the 26th, 1945, 3 days after Wilson's bridge at Wehrmacht was completed, the German situation in Italy had become hopeless. Allied forces were across the Po in strength, German rearguards were being overrun, supply lines had collapsed, ammunition was running out, fuel was exhausted, units that tried to make a stand were bypassed by Allied armor moving cross-country. Units that tried to retreat found their escape routes cut off by Allied spearheads that had crossed the river ahead of them. On April 29th, German commanders in Italy began surrender negotiations. SS General Karl Wolff and Wehrmacht General Heinrich von Vietinghoff met with Allied representatives in Switzerland. By May 2nd, all German forces in Italy had surrendered unconditionally. Over 900,000 German and Italian fascist troops laid down their arms. It was the first mass surrender of German forces in World War II, occurring 5 days before the general German surrender on May 7th. The speed of the collapse shocked everyone, including Allied commanders. They had expected the Po River line to slow the German retreat significantly. They had planned for German forces to establish defensive positions along the Adige River and fight for weeks. Instead, the entire German defensive structure in northern Italy disintegrated in a week. The Bailey bridges were a major factor in that disintegration. German units simply could not establish defensive lines when Allied forces could cross every water obstacle within hours. Military historians analyzing the Italian campaign identified the Po crossing as the decisive operation. Earlier battles, Monte Cassino, the Gothic Line, the Argenta Gap, all of those were important. But the Po crossing was the stroke that ended German resistance, and the Po crossing succeeded because Allied engineers could build bridges faster than German forces could retreat. Donald Bailey lived quietly after the war. He returned to his work at the Road Research Laboratory, the post-war successor to the experimental bridging establishment. He consulted on bridge designs. He advised on international standards for military bridging. He attended reunions of Royal Engineer units that had used his bridge in combat. He always insisted that he had simply created a tool. Others had used that tool to win the war. In 1985, Bailey died at his home in Bournemouth at the age of 83. His obituary in the Times of London noted that his bridge had been used in every theatre of the Second World War and remained in service with military forces worldwide. Field Marshal Lord Carver, former chief of the British Defence Staff, wrote that Bailey had done more to help win World War II than many generals whose names were better known. The Felonica Bridge that Lieutenant Colonel Wilson built on April 23, 1945, remained in use after the war. It became a permanent road bridge, serving local traffic across the Po River for over 20 years. Eventually, it was replaced by a modern concrete structure. The Bailey panels were salvaged and reused elsewhere. Some may still be in service today, part of a mining road in Africa or a farm bridge in Asia. Bailey panels were built to last. There is no memorial at Felonica marking where Wilson's bridge stood. The local population remembers the liberation, but not the specific bridge that helped to make it possible. That is typical of military engineering. The structures are temporary. The impact is permanent. The battles are remembered. The bridges are forgotten. But for the German soldiers trapped south of the Po River in April 1945, those bridges were unforgettable. They represented the moment when their retreat became a trap. They watched Allied tanks roll across spans that should not have existed. They realized that no matter how far they ran, Allied engineers were faster. The Bailey Bridge was not a weapon that killed them. It was a tool that caught them. And that was Donald Bailey's genius. He did not design a weapon. He designed a solution to a problem. How do you cross a river quickly when the bridges are gone? His answer was so simple, so elegant, so effective that it changed the nature of warfare. Armies that possessed Bailey bridges could move faster, strike harder, and exploit opportunities that other armies could not. Rivers stopped being obstacles. Terrain stopped being decisive. Speed became everything. In the history of military technology, few inventions had such immediate and widespread impact. The machine gun changed tactics. The tank changed battlefield mobility. Radar changed defensive capabilities. But the Bailey Bridge changed operational tempo. It accelerated warfare. It made rapid advance possible over any terrain. It turned retreat into rout, because retreating forces could not break contact. The title of this video suggests one engineer's insane bridge trick trapped 2,000 Germans in 12 hours. That framing is not entirely accurate, but it captures a deeper truth. The Bailey Bridge, designed by one quiet civil engineer working in a British laboratory, ultimately trapped hundreds of thousands of German soldiers by eliminating time as a defensive resource. The 12 hours it took to build a bridge at Felonica was repeated hundreds of times across Italy in April 1945. Each bridge trapped more Germans. Each crossing accelerated the collapse. Lieutenant Colonel Wilson, standing on the south bank of the Po River on April 23, 1945, did not know he was participating in the final act of the Italian campaign. He was just trying to build a bridge fast enough to keep the advance moving. He succeeded. His engineers succeeded. The Bailey Bridge succeeded. And the German 10th Army ceased to exist. That is the real story. Not one bridge, not one engineer, not 12 hours, but a system, a design, a capability that changed how armies moved and how wars were won. Donald Bailey's modular steel panels, carried by soldiers, assembled by hand, built under fire, became one of the most important innovations of the Second World War, not because they were complex or revolutionary in concept, but because they worked. Reliably, quickly, everywhere. The panels were still being manufactured in 1945 when Bailey bridges in Italy helped end the war there. They were manufactured in 1950 during Korea. They were manufactured in 1965 during Vietnam. They are manufactured today for military forces and civilian applications worldwide. 80 years after Bailey sketched his original concept, his bridge remains in production. Few military technologies can claim that longevity. And every time a Bailey Bridge is erected, whether by soldiers in a war zone or engineers responding to a natural disaster, the process is the same. Panels are carried forward, pins are hammered in, the structure extends. In hours, a crossing exists where none stood before. It is simple, it is effective, it works. That was Donald Bailey's gift to the world. Not complexity, but simplicity. Not specialization, but universality. Not slow precision, but fast adequacy. The Bailey Bridge was good enough, strong enough, quick enough. And in war, good enough is often better than perfect. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.